Just imagine a sky where the most advanced multi-billion-dollar stealth bombers are completely visible. For decades, military dominance has relied on invisibility. These aircraft are coated in classified materials, shaped to deflect signals, slipping through enemy defenses without a trace. But what exactly happens when that invisibility cloak is suddenly ripped away, and a new technology does not just detect the aircraft, but makes it mathematically impossible for the pilot to hide or jam the signal? The balance of global power would shift overnight. This is the promise of the quantum radar system. It sounds like science fiction, an ultimate weapon drawn from the deepest, highly classified laboratories. Yet the physics are very real, and the race to build it is already underway. Are we on the verge of a new era of warfare, or is this ultimate sensor hiding a fatal flaw? To understand why the military desperately needs quantum radar, we first have to look at the massive vulnerabilities of current air defense systems. Classical radar systems rely on bouncing radio waves off a target and waiting for the echo. But modern stealth technology defeats this by using geometric shapes to scatter those waves and specialized radar-absorbing materials to swallow the rest. Even worse, modern electronic warfare can create digital ghosts. Adversary spoofing platforms can mimic radar signals, flooding defense screens with fake targets. This creates a terrifying and expensive problem. When an air defense network cannot tell the difference between an electronic decoy and a real threat, it is forced to launch multi-million-dollar surface-to-air missiles at phantom targets. This drastically reduces the cost per kill metric, bleeding a military dry both financially and tactically. Radar platforms operate via continuous area denial illumination rather than finite magazines, so eliminating false positive kinetic engagements is the primary economic advantage of a functional quantum radar. The economic stakes are absolutely massive. Extensive global investment is currently pouring into the quantum sensing sector. According to QY Research, the global quantum radar market valuation reached $417 million in the year 2025. Projections scale this to over $1,298 million by 2032, representing an 18.3% compound annual growth rate. The broader quantum warfare market is projected to expand from $2.34 billion in 2026 to a staggering $10.44 billion by 2033. Right now, current iteration quantum radar units operate as high-value experimental demonstrators rather than mature production assets. In 2025, global production yielded approximately 325 operational demonstrator units, with an average procurement cost of $1,280,000 per unit. But what exactly are these millions of dollars buying? How does this experimental technology actually strip away the shadows of modern combat? To find out, we must look inside the most extreme, freezing environments on Earth, where the brutal realities of physics govern everything. The true cost for mature, fully weaponized battlefield iterations remains locked away, with data unavailable to the public. But the fundamental components required to build them tell a story of incredible complexity. The foundational architecture of a quantum radar system relies on microwave quantum illumination protocols. Unlike classical radar architectures that utilize coherent radio frequency oscillators, quantum radar generates non-classical two-mode squeezed vacuum states. This incredible feat is executed utilizing Josephson parametric amplifiers, or JPAs. These JPAs are situated within extreme cryogenic vacuum chambers, producing highly correlated, entangled microwave photon pairs. These pairs are functionally split into a signal beam and an idler beam. The system executes signal transmission by projecting the signal photons toward a suspected target space. Meanwhile, it preserves the entangled idler photons in a localized quantum memory module. When signal photons reflect off a target and return to the receiver, they undergo microwave to optical transduction via electro-optomechanical converters to preserve the quantum states for analysis. Receiver architectures utilize optical parametric amplifier, single photon avalanche diode systems. Detection processes employ some frequency generation for joint measurements, allowing the system to execute digital phase conjugation for computational correlation recovery. This isolates the residual quantum discord from extreme background thermal noise. The tactical advantages are profound. Quantum illumination operates independent of geometric deflection. Relying on the statistical correlation between entangled signal and idler photons, any reflected photons returning from the target area can be positively identified as belonging to the original transmission. This nullifies stealth technology by increasing the effective visibility of low observable airframes. Furthermore, the physics of the no-cloning theorem dictate that an unknown quantum state cannot be perfectly copied. Adversary electronic attack suites cannot replicate the entangled signature of emitted photons. Spoofed radio frequency energy is mathematically discarded by correlation algorithms, rendering classical jamming techniques completely obsolete. Theoretical foundations confirm that quantum illumination achieves detection performance exceeding classical limits by up to 6 decibels in the error exponent, an advantage pronounced in high-noise environments. Additionally, quantum radar systems operate utilizing exceedingly low power outputs, often functioning at the single photon emission level. This minimizes electromagnetic emissions, masking the radar site from adversary radar warning receivers and anti-radiation missiles. But here is the crushing reality. The overarching constraint of the hardware is thermal management. Core components must be continuously bathed in liquid helium to maintain temperatures in the millikelvin range. Structural housings utilize advanced composite isolation materials to mitigate acoustic and thermal shock. To preserve quantum coherence, the internal architecture mandates heavily shielded superconducting nanowire single-photon detectors. The cryogenic cooling plants required to maintain these temperatures generate massive quantities of waste heat and demand immense industrial power supplies. The continuous consumption of liquid helium and the constrained operational lifespan of superconducting components drive long-term sustainment expenditures into the tens of millions annually per operational node. Due to these thermal management requirements, the size, weight, and power footprint of quantum radar prohibits tactical mobility. The technology is strictly confined to massive, static ground-based installations or naval vessels with nuclear power generation capabilities. Airborne deployment on fighter-sized platforms is currently barred by thermodynamics and physics limits. Entanglement between photon pairs is exceptionally fragile. Atmospheric moisture, precipitation, and environmental thermal noise cause signal photons to interact with the environment, rapidly destroying their entangled state before they return, a process known as quantum decoherence. Additionally, quantum radar remains subject to the inverse square law. As photons travel and reflect back, the beam diverges and suffers extreme path loss. The volume of surviving signal photons returning to the receiver is astronomically low compared to the overwhelming influx of background thermal microwave photons. With such immense physical limitations, we must ask, has anyone actually made this work in the real world? The true story of quantum radar testing is a battlefield of bold claims and harsh scientific realities. In September 2016, the China Electronics Technology Group Corporation published press releases claiming the successful development and testing of a working quantum radar demonstrator. They claimed it achieved detection ranges up to 100 kilometers. However, Western defense researchers heavily scrutinized this claim due to the physical improbability of maintaining quantum coherence over such vast atmospheric distances. However, the verified technical failures paint a very different picture. Extensive peer-reviewed engineering assessments published between 2022 and 2026 rigorously document the failure of long-range aerospace quantum radar. Field demonstrators routinely failed to detect targets at hectometer or kilometer ranges. In fact, they yielded operational ranges of approximately 1 meter, performing worse than standard, low-cost marine noise radars. Because classical signal processing cannot achieve quantum discord recovery, the system integrates machine learning algorithms to compute quantum Chernoff bounds. These algorithms attempt to identify faint quantum correlations amidst massive classical noise. Acknowledging the absolute barrier of atmospheric decoherence, global defense agencies have executed a strategic shift. Funding has shifted away from long-range, stealth-defeating aerospace radar toward integrated short-range quantum sensing, such as quantum magnetometers for undersea submarine tracking and quantum cryptography. In August 2023, Innovation, Science and Economic Development Canada initiated contract funding for quantum sensing prototypes tested in real-life settings, officially pivoting focus from theoretical long-range radar to verifiable short-range sensors. Currently, the official project roadmap for deploying a pure long-range quantum radar capable of aerospace stealth nullification is officially stalled. The test and evaluation status for long-range deployment is marked as data unavailable. Instead, the future lies in hybrid integrated sensing and communications frameworks, synthesizing weak quantum returns with traditional data streams to produce targeting quality tracks. These frameworks are actively progressing toward test and evaluation in the 2028 to 2032 window. This monumental effort involves heavy collaboration between government agencies like the Defense Advanced Research Projects Agency, Canada Department of National Defense, the Royal Navy, and the United States National Quantum Initiative. Prime aerospace and defense contractors engineering the underlying component technologies include Lockheed Martin, Northrop Grumman, L3 Harris Technologies, Raytheon, and Thales Group. Sivers Semiconductors and Agnet Semiconductors are also documented collaborators supplying advanced transmission architectures. The dream of unmasking the skies remains alive, shrouded in classified shadows. The future of aerial warfare is clearly shifting, moving from traditional kinetic dogfights into the invisible subatomic realm of quantum mechanics. Now, I want to hear your thoughts on this rapidly evolving battlefield. Do you think military funding should continue pouring into massive, complex quantum sensor installations? Or should defense agencies focus their budget strictly on traditional stealth aircraft and conventional electronic warfare systems? Drop your personal military technology preferences in the comment section down below. If you want to keep exploring the brutal realities, the advanced physics, and the cutting-edge engineering of future warfare, make sure to hit the like button and subscribe to the channel right now.